These diagrams are taken from Dr. Phil Playfords' book published in 2013 called The Geology of Shark Bay. This diagram is a beautiful diagram about Fief stromatolites. So we've looked at Fief stromatolites in the Boulder province, and we talked about them forming in long lines, in long rows that are subparallel to shore. And the reason for that is because of the wind direction. The wind direction dominantly comes from the south to the north. And when that happens, it rips across the water, especially during the summer when the waters are very warm and you have really low tides. That wind direction induces paired helical vortices, which are known as Langmuir circulation. That enhances the long Fief structures. In the image on the right, it shows old Pleistocene beach ridges, so ridges that are formed about 120,000 years ago, and those form topographic highs. Stromatolite building microbial communities like to grow on hard topographic highs because that gets them a little bit off of the seafloor, that keeps them out of the sand that moves around with the water. Because if you can imagine, if microbial mat colonizes mobile sand communities, then anytime that sand gets churned up, that microbial community gets broken up. That mat is not able to retain its cohesive structure when waves and sands are moving. So microbial community often colonizes that topographic high to get it out of that movement. So often you find that stromatolites are building over old relict Pleistocene highs. This slide is an image from the Boulder province, and you can really see this is about about a kilometer. At the top is the main camel dray track where the camel used to walk out and bring the wool. So we walked down that track to get out to the subtidal stromatolites. But you can see that the whole area is dominated by these long Fief stromatolites. And as you move towards shore, these gray lines are an indicator of old stromatolites that are no longer accreting, but are on top of those old Pleistocene highs, those old dunes. And so that's why they're forming in those ridges. Also, the Fief stromatolites have these tuning fork junctions, which are also a good indication that they're driven by wind and Langmuir circulation. So you can see the Y shape in the image on the right. In the image on the right, if you look to a lot of the stromatolites, those long Fief stromatolite bands, they have tuning fork junctions, or these inverted Ys, which are also an indication of being influenced by wind. If you look at this image, you can see at the top of this rock structure, you've got huge boulders. We believe these boulders were placed there by a tsunami. In fact, a mega tsunami that had to have enough power and enough force to get those huge boulders up onto the top of that structure. In Hamlin Pool, there's also a lot of evidence of a mega tsunami. Around the southeastern margin, you've got a very large coquina ridge, which is thought to have been put there by the mega tsunami. This is evident just behind the telegraph station. The big ridge that you have to climb over to get to the stromatolites is thought to be a mega tsunami deposit. Additionally, stromatolites accrete at very slow rates. And we believe that the stromatolites have grown in Hamlin for about the last 2,000 years. Based on our current knowledge of stromatolite growth rates, some of the stromatolites are way too big to fit within that structure. So one of the ideas that we have is that possibly large boulders were moved into Hamlin Pool during a mega tsunami, and the stromatolites accreted on top of those structures to form massive stromatolites. So the idea is that quite possibly not all of the stromatolite is microbial growth. Some of it may be a large boulder nucleus that stromatolites have grown on top of. And this I'm talking about stromatolites that are over 1 meter in height or 1.5 meters in height. The image on the left shows the salinity regime of Shark Bay. So towards the mouth of Shark Bay, we've got open oceanic type of salinity, so around 35. As you move deeper into the bay, you get metahaline waters, which are quite salty. And then down into Hamlin Pool and Laird and Bight, you have hypersaline waters. Hamlin Pool has an average salinity of 66 parts per thousand. In the right image, you can see the dominant wind direction. And in the summer months, the dominant winds in Hamlin Pool come from the south and from the southeast, which is really important when we think about Fief stromatolites and how they line up. Also, in the winter months and in the afternoons, you get strong winds that come from the west. These winds pull water away from the western margin of Hamlin Pool and pile it on the east. 20% of the tides in Hamlin Pool are due to astronomical forces. 20% are a result of the seasonal differences, rain and evaporation. In the winter months, you have higher high tides and higher low tides because the water is overall higher. And in the summer, you have lower high tides and lower low tides because of the evaporation and not a lot of rainfall. So the overall water in Hamlin Pool is lower in the summer months. The remaining 60% is a result of meteorological forces, which is the wind. The water level in Hamlin Pool is controlled 20% by astronomical forces, 20% by seasonal effects, and 60% by meteorological forces like the wind and local pressure system.